All right. The question number one was pretty much just looking at the chart. All these species are on the chart. And so if you take a look at the acid chart here, let's see. This chart's the same as the one that I handed out. You'll have the chart also on the test. But if you look, iron 3 plus is the strongest, and then HF, and then acetic acid. And what else was there? Methane. Methane's the weakest. Methane's on our chart as the weakest. So just consult the chart. Number 2, 0.100 molar selenic acid. Selenic acid is a strong acid here. Selenic acid is like sulfuric acid. Sulfuric acid, Ka1 for sure is going to give you the most H+. But when you look at Ka2, like for sulfuric acid, Ka2 is 0.021. For selenic acid, it's even bigger at 0.022. And so when we look at how much hydronium comes from step 2, it's significant. About 10% of the hydronium in sulfuric acid comes from step 2. And so selenic should be about comparable, around 10 plus percent should come from step 2. So we're going to get around 0.11 molar hydronium from this. So there's significant quantity of hydronium from step 2. If you're not sure, you just do step 2 and you see. Kw is not going to give any significant hydronium to this because the most Kw will give is less than 10 to the minus 7 molar, which is not going to impact that. And so B is the correct answer, Ka1 and Ka2. For a lot of acids, though, just Ka1 is enough. But you have to look at Ka2. If it's like 10 to the minus 2, it's significant. Stop me if you have any questions on these. Okay, number 3. Let's see. Look at number 3 on 1 times 10 to the minus 8 molar HCl solution. Page determination required. So 10 to the minus 8 molar, it's a strong acid, so it's going to give us 10 to the minus 8 molar H+. But 10 to the minus 8 molar is very small. And since it's very small, we have to consider Kw too. And so this is the example we did in class. Do you recognize it? You should know how to do that calculation in class. Like all the calculations we do in class, you should know how to do it because even then, a lot of people will say the pH is 8. pH can't be 8 in an acid solution. 8 is base. 4. To the equilibrium, HBr, okay, so HBr is a strong acid. If we have a strong acid here, it's just a one-way reaction. We've talked about that before. And so Ka is very large, so there's no shift. Even though, if this is a regular equilibrium, then if we add additional bromide, it should shift it left, right? But this is a special circumstance where strong acids. Strong acids are strong electrolytes. Strong acids, strong bases, and soluble salts are not going to shift. Le Chatelier's type shift. 5. Circle all amphoteric species. Amphoteric species can lose or gain a proton. So if this loses, we form carbonate. If it gains, we form carbonic acid. If this one loses, we form amide. If it gains, we form ammonium. If this one loses, we form oxide. If it gains, we form water. If this one loses, we form hydroxide. And if it gains, it forms hydronium. So all of these species are amphoteric. All these species occur on both sides of the acid-base chart. And so pH varies from minimum of 0 to maximum of 14. No, that's false. We can go below 0. We can have negative pHs, and we can have pHs greater than 14. It's just when we go outside that range, what do we have to worry about? If we're outside the range from 0 to 14, we should start to worry about what? Yeah, good. We have to worry that they aren't going to behave ideally. All right, I didn't have that much time, but which base is strongest? So what I look here is, we have the carboxylate group here, the COO minus group. And then we have two different attachments to the carboxylate group. This is RC, the carboxylic acids, when they get deprotonated, they form the carboxylate group like this. And so we look at the R group that's attached to our carboxylate group. And usually for R groups, we look, is it electron rich or electron poor R group? And so the two R groups that we're looking at here is, one is a methyl in acetic acid, and the other R group is a trichloromethyl group. A trichloromethyl group has just chlorines instead of the hydrogens here. And these are going to be, carbon, you think, carbon's carbon, but no, carbon's not carbon. But these two carbons are quite different. When you look at the two carbons, what's the difference here? Well, there are different ways you can analyze the difference here. One way to analyze the difference is, now you have these electronegative chlorines versus the hydrogens. Carbon-hydrogen bonds is pretty non-polar. This whole thing's pretty green. But these chlorines here are quite polar. Not polar in that sense. They're quite electronegative, which makes them quite polar. That is, they're going to withdraw electron density and make these delta minus, right? And that's going to make the carbon a lot more positive here. And so that's one way of looking at it. Another way of looking at it is, I think of this carbon as being electron rich and this carbon as being electron poor. Why? Rebecca? Yeah. We can look at it based on oxidation state as well. This carbon's bonded to carbon. So carbon bonded to carbon, it's split electrons. So how many electrons does carbon end up with in this structure? What's the oxidation state of that carbon? When this is bonded to another carbon here, it's a tie. And so count the electrons. Here, I'll put the carbon in there. This is the R group here. The R group is this. This carbon's not considered the R group. If you still haven't figured out how to do oxidation states, you should, ask for more examples or do something. Don't wait until the night before the final exam to try to figure it out. If you can't do these quickly and easily, then try to correct that. This should be easy. The oxidation state, what is it? Should be easy. But if it isn't, make sure, by the time the final comes, it's easy.
the same thing with this one here. The methyl group is what we call a radical. You know, the methyl group looks like this. It has a dangling bond. Like this lone electron.
Dangling bond. That's the methyl group. This is a trichloromethyl group. It would have a dangling bond there, and then you just attach it. In organic chemistry, that's what's commonly done. We call these substituent groups. And we like to look at the substituents, you know, what's their character. One of the things we like to look at, are they an electron withdrawing substituent or electron pushing substituent? The difference is electron withdrawers are poor, electron poor. The electron pushers are electron rich. That changes the behavior of these things. So is methyl electron rich or electron poor? In general, hydrocarbons are electron rich. Electron rich, in the redox chemistry, you have the fuels and you have the oxidizers. The fuels are going to be electron rich, the oxidizers are going to be electron poor. And so if something's a good fuel, like hydrocarbons, then they're electron rich. That's the way we think of it. Don't be shy. At least one person knows how to do oxidation states in their head. Negative one? Not negative one. Plus 3? Not plus 3. Close. Negative 3. Yeah, good. So this is negative 3 on this one, which is on the electron rich side. So this is considered electron pusher. Electron pusher here is going to make this whole thing more negative. You know, you're pushing, and this is the carboxylate group. Carboxylate, you know, so you got the resonance structures for this. It's actually minus 1/2 on each oxygen. But, you know, it's going to make this what we call more blue or more red. Well, actually, negative is what color? Red. And so if this is electron pusher, it's going to make this more red. It makes this more red. If this is more red, then bases are red. And the more red it is, the more basic it is. So electron pushers make things more basic. Well, whereas over here, what's the oxidation state here on this carbon? Plus 3. Okay, that's good. Just a bit down. That's not a double bond there. But you want to get to that level, you know, and there's no reason you can't get to that level. I mean, it's not that complicated. It's a matter of dividing the electrons up and counting them. So it's nothing special. This kind of stuff, you know, figuring out oxidation state can go to AI or whatever. You know, this is one of the jobs. If your job was to count oxidation states, then you might be in danger of losing the job to AI because it's not that hard to do. But the thing that you might not lose to AI is how you interpret the oxidation states, because that's a little bit more difficult, I think. And I've trusted AI, you know, like ChatGPT and stuff. So it's still learning. So it's not quite there. So it's still safe. But anyway, plus 3 means it's on the electron, what? Poor side. Electron poor side means it's sucking electron density from this. If it sucks it, then it's going to do what? This is red, and it's going to make it turn blue? No, it's not going to make it turn blue. What it's going to do is it's going to make it less red. And the less red it is, the less basic. And so we look at the substituent groups and then figure it out. And so this for sure is going to be the most basic here. Is acetic acetate versus trichloroacetate. The percent ionization of acetic acid decreases as the concentration increases. Okay, I didn't really talk about this. There's a graph in the book that shows this. And the graph in our book that shows this plots the percent ionization as a function of the initial concentration. So as the initial concentration of acetic acid increases, the percent ionization decreases. It's not linear, it's nonlinear function like this. So at the limit of infinite dilution, we have infinite ionization out here. Which is that. And so the percent ionization of acetic acid decreases as concentration increases. Yes, that's true. As concentration increases, we see a drop in the percent ionization here. I talked about this briefly when I was talking about the percent ionization is not a fixed number. If acetic acid had a constant percent ionization, then our calculations would be easy. But since the percent ionization or the percent reaction depends on the concentration initial, we have to do the calculation. And so we can't use, this is when we were originally looking for patterns to predict. And so we can't predict it based on a fixed percent ionization, because a fixed percent ionization is not there. I just didn't tell you which direction. I think I did mention it, but I didn't. Actually, I'm pretty sure I did mention it. This is just kind of recall. Which species is more acidic? And so when I analyze something like this, I look at NO2. NO2 is called the nitro group, in organic chemistry. This would be the nitro substituent. And so if we look at the nitro substituent, let's look at the Lewis structure of nitro substituent. And so we have, this is bonded to a carbon here. And the nitro substituent, we can draw out like this. The nitro substituent, let's take a look at how many electrons that we have here. Nitro substituent is kind of weird here. We have an octet around nitrogen. We have octets. We all have octets here, but the formal charges are weird. What are the formal charges here in the nitro group? So formal charges should be very easy too. Yeah, give me the formal charge on nitrogen. +1. And the formal charge on this oxygen? -1. And then we have a resonance form for this. What would you consider the nitro group to be? Electron pusher or electron withdrawer? What are the three most electronegative elements on the periodic table? Fluorine, oxygen, and nitrogen. That's a nitrogen with a 0 formal charge. If you had a nitrogen with a positive formal charge, it's going to have an even higher electronegativity than normal. And so fluorine is a 4O, oxygen is 3,5, nitrogen is a 3, but this is going to boost it because of that positive formal charge. Okay. Plus the oxidation state. What is the oxidation state of nitrogen in this nitro? +3? Yeah. The oxidation state's +3.
3. It's going to get these 2. It normally has 5. It's going to lose all these to oxygen. And so it only ends up with 2 electrons, so it's plus 3. Good. A plus 3 is kind of high, right? And so this is going to be electron withdrawal. So the formal charge we can see for sure has a positive charge, but it also has a plus 3 oxidation state. Oxidation states I show in parentheses, formal charges I show circle. In organic, they pay particular attention to formal charges. It's important. And the same thing. So what would you say? The nitro group is electron withdrawer or electron pusher? It's electron withdrawal. But you know, we have nitro groups here. So, but then we have this. Do you know what this ring is called? This is a benzene ring. And it turns out that phenol, which is this, is, you know, most alcohols have a very, very small, like a negligible Ka. So if we compare, let's compare like acetic acid. Here. Is this working? No. Let's compare acetic acid here to ethanol. You know, both of these have the COH, you know, and this is going to be a polar bond. Oxygen is 3.5, hydrogen is 2.1, so that's polar covalent. Oxygen is 3.5, hydrogen's the 2.1. This is also polar covalent. When we calculate the delta EN for this bond is exactly the same as the delta EN for this bond. And so you would think that these hydrogens are equally red, but they aren't equally red. One hydrogen is a lot more red than the other. Which one is it? It turns out this hydrogen is a lot more red. Why? What we have to do is we have to look not just here, but we also have to look at what this is bonded to. What this is bonded to is a carbon. What this is bonded to is a carbon too. So it's both bonded to carbon. Carbon's electronegativity is a 2.4, 2.5. But then we have to look at what is the carbon bonded to. And so when I look at this, I look at this carbon, and I look at that carbon, and I go, that carbon's electron poor. When I look at this carbon's a lot more electron rich. Can you see that right off? You know? Or we think in terms of the inductive effect. In terms of the inductive effect, that oxygen is going to be sucking electron density away from this carbon, making this carbon more poor. But we can also see it in terms of the oxidation state. I just look at the oxidation state, and that tells me, what's the oxidation state of this carbon here? +4? +4. Let me exit out of this slideshow. I'm right on this. You know, normally and you'll find this, a lot of professors don't bother reviewing. If you didn't catch it, they're just going to keep moving on because there's not enough time to go back over and over and over it again, you know. But I think that this is pretty important, just in general. So winner take all unless it's a tie. So oxygen takes all the electrons, carbon versus carbon's a tie. How many electrons does carbon end up with? 1 electron. How many is it supposed to have? 4. So it lost how many? 3 plus 3. That's the oxidation state there. It should be, you know, you want it to be pretty easy. How many, how many electrons does carbon end up with here? 7. It's supposed to have 4. It gets -3. You want to get to the level where you can just look at it and say what the oxidation state is. That would be good. And you can see this is quite electron rich. This is electron poor, right? This carbon. These two carbons are on the opposite ends of the spectrum. However, when we look at this carbon is the same as that carbon, -3. But this carbon, what is this carbon? I did this count at 2, 4, 5, -1. And so this is quite a bit richer here. And so +3 carbon is going to be withdrawing a lot of the electron cloud density from this. This is going to make this much more red than this. An oxygen-hydrogen bond enthalpy is about the same in both, right? Pretty much we treat them the same. So the bond energy is the same. So we just look at polarity in that case. So bond energy is number 1. Number 2 we look at is polarity. This one is quite a bit more red than this one. Take a look at the acid strength difference. This is 10 to the -5 acetic acid, but ethanol, 10 to the -16. 10 to the -16 is 10 to the minus, or, well, the difference here is 10 to the 11th. 10 to the 11th is 100 billion. So ethanol is 100 billion times weaker than acetic acid. And acetic acid is already considered a weak acid, so what would ethanol be considered? Ethanol wouldn't even be considered an acid. People don't usually consider ethanol an acid because it's so weak. It's too small. And so alcohols aren't normally considered acids. So, a couple of things regarding this. Alcohols in general are very weak. R group, usually the bonding atom is carbon or hydrogen here in the R group. And if it's carbon, then we can have longer chains. And then we have an OH. Okay, this is alcohol. And that carbon can't have a double bonded oxygen because an alcohol has to be contrasted with an acid here. If we look, an acid has what we call a alcohol group. This is the alcohol group. But in addition to the alcohol group, it has a C double bond O group. Do you know what a C double bond O group is called in organic chemistry? A C double bond O is called a carbonyl group. Like carbon monoxide is a ligand, carbonyl. So it's a carbonyl group. And so this is quite a bit different. What happens here is this becomes much deeper, red here, this proton, whereas this proton is not nearly as red. And so if you're a base, you're going to see this one. And the bond strength is comparable, so this one's going to be a lot easier. The base can get a grip on this hydrogen here because a base is negative, so this is quite positive here. And this one isn't. So we could either show it in red or we could show it in terms of delta pluses and delta minuses. In terms of delta pluses and delta minuses, this is a big delta plus here, which is fine. This is a much smaller delta plus. Although, in terms of hydrogen bonding and that type of thing, we always think of this as being an unusually large delta plus, because if you go back to Chem 1A, hydrogen bonding comes from having a partially exposed proton. In other words, they call it the D-shielded proton. Do you guys remember the D-shielded proton in hydrogen bonding? So this is almost a full positive charge, right? Already. So this is already a big delta plus. But in comparison to the carboxylic acid, this is a heavily de-shielded proton, and this is still quite de-shielded here. So alcohols in general, because alcohols, the R group is usually electron rich. You know, hydrocarbons are electron rich. And so we should put that there. That's why hydrocarbons are so flammable. You know, and gasoline is a mixture of hydrocarbons. These are typically electron rich. But even though they're electron rich, we see something interesting happen with some of these here, which I wanted to talk about now. Let me save this before it crashes. So a benzene ring can be written in different ways. This is one way of writing it, which is equal to writing it like this. You know, because normally we have two resonance forms for the benzene ring. In organic chemistry, sometimes they leave off the hydrogens and just show the carbon bonds. And so when we look at this benzene ring here, really we're seeing a hexagonal ring of carbon atoms with alternating double bonds. And then we have these hydrogens. These are all sp2 hybridized carbons, and they're all going to be trigonal planar like this. Now, double bonds are shorter or longer than single bonds? Double bonds are shorter. And so you'd expect this to be a distorted hexagon, but it's not distorted at all. It's a perfect hexagon. Why is that? If double bonds are shorter than single bonds, why isn't this hexagon distorted? Because neither of these resonance forms are accurate. The hybrid is the most accurate. So this is just trying to represent the hybrid. I think I screwed this up. So when you remember the sp2 hybridization, we have sp2 hybridized orbitals in a trigonal planar arrangement. And so we have three sp2 hybrid orbitals like this. And then perpendicular to this, we have a p orbital that's unhybridized. Unhybridized p orbital. And so what we see is we see the double bond occurs when we have the overlap of the pp orbitals to form pp pi bonds like that. But since all these p orbitals are all lined up, we can have delocalization over the entire structure of the pi bonding. Component of the double bonds. And so what we have is we have complete delocalization over the entire structure here. So benzene burns easily, you know, it's electron rich. But an interesting thing happens when we look at this. Phenol doesn't behave like a normal alcohol. This is unusually acidic. Why is it unusually acidic? Is it because it's more red? No. It's not because it's more red, because this is kind of electron rich, right? But the weird thing is that even though it's electron rich, the benzene ring is considered an electron withdrawer. The way we can see that it's electron withdrawer is it's electron withdrawer because of resonance delocalization. And so let's do this. Let's take the phenol and we'll have a base come along and pluck the proton off like water. And then leave these electrons behind here. And then we form hydronium. And the conjugate base of phenol. Do you know what the conjugate base of phenol is called? What's the conjugate base of ammonia called? Do you know? Conjugate base of ammonia? Not ammonium, that's a conjugate acid. No, not amine. Amide, yeah, or amide, that's it. Do you know what the conjugate base of methane is called? Methide. And so what do you think, or the conjugate base of hydroxide? Oxide. Do you see a pattern? What do you think the conjugate base of phenol is called? Well, I'll just tell you. Phenoxide. The "ide" ending. So that's it. The same thing with alcohols. What do you think the conjugate base of ethanol is called? Ethoxide. Ethoxide. So if a base were to come and pluck the proton, it'd be very difficult, but a base could do it. If a base comes along and plucks that proton off ethanol, we form ethoxide. So ethoxide, methoxide, all the alcohols are similar in that sense. And so phenoxide is a very interesting species because let's take a look at what happens. In ethoxide has trouble with this charge. And so we're going to compare this to ethoxide. So a conjugate base of ethanol, that is, ethanol loses the proton. And makes ethoxide. Ethoxide is very blue. Is it what? Blue is, no, wait. What is red? I mean, red and blue. Actually, did I screw it up? No, I don't think so. This is red, right? Negative is red. This is very red. Because what happens is, this is called an ethyl group here. This ethyl group, 2 carbons, is it electron rich or electron poor? The ethyl group.
electron rich. If it's electron rich, it's going to try to push negative charge density towards the oxygen. It's electron pusher, which is going to make the oxygen more or less red. More red. And so this is a powerful base. It makes sense because ethanol is a worthless acid, therefore its conjugate base must be extremely powerful. I don't know if I should say powerful might be too strong a word. Let me just say strong. This is a strong base. It's not one of the strong bases you had to memorize. This is a strong base that you'd be able to determine from the structure. In fact, I'd expect this base to be stronger than hydroxide or weaker than hydroxide? Stronger. Because we saw one. Do you remember what example did we see just recently? Another strong base that's stronger than hydroxide. The example I gave the other day was methoxide. Do you remember that? Methoxide? Methanol? Oh, okay. It was from the other day. So this is kind of recall. But it's a little bit more than just recall memory because we could figure it out. This should be probably stronger than methoxide. Because methoxide only had one methyl and this has an ethyl. Right? But the carbon chain length doesn't have a major impact because the further you get from this. So if I went to propoxide, this is ethoxide with 2 carbons. If I had a third carbon, propoxide, let's say, it's not going to make a huge difference because the further out we get from this, the less of an impact it does. But it will have a little bit of an impact. So chain length does have a small impact on it. So if we go back here, let's take a look at another example here. So here we can take a look. This is acetate here with just 1 carbon. So this is a methyl kind of attached to the carboxylate group here. But now we got 1, 2, 3, 4, 5, 6, 7 carbons attached. And this is quite electron rich, right? It's an electron pusher, but did it make it all that much more basic? In fact, when we compare the two, which one looks like to be a stronger base? This is screwed up because I wish they didn't do this. Here. So this is the Ka, but this is not an acid, right? We should be looking at the Kb. And so if we compare the Kb's, which one has a bigger Kb? Rebecca? The second one. The second one. Remember, we have the inverse relationship. So this has a stronger Ka, which means this is 1, 2, 3, 4, 5, 6, 7, 8 carbons. Do you know what we call an 8-carbon carboxylic acid? Eight carbons is, what prefix do we use for 8 carbons, or parent? Oct. This is called octanoic acid. And 2 carbons is called ethanoic acid, but nobody calls this ethanoic acid because it goes by the common name acetic acid. Here. Is it all that much stronger though? This is marginally stronger. It's about the same. Do you see that? And so even though we're adding a whole bunch of electron-rich carbons, it's not making a huge impact on this because it's so far away. So distance does play a role. Uh-huh. Okay, I'm sorry. Can you repeat that first part again? No.
Now, hydrocarbons aren't necessarily very, very strong acids. Like carboxylic acids are, in general, weak acids, but much stronger than alcohols. And so they aren't really strong. They're just stronger than alcohols, a lot stronger than alcohols. And so it's just relative. But compare these. There's one, though. There are a number of carboxylic acids that are in the strong acid category. Let me tell you one of them. This one is a borderline strong acid. Can you tell me why? This one is, some people consider this one a strong acid. But you just memorize the 7 common strong acids, right? You don't memorize all of them. This is the same thing with the bases, but you should know something structurally to help guide you. You would expect this to be a lot stronger or a lot weaker than this as an acid, let's say. Acetic acid versus this. This is not acetic acid, by the way. I don't know why they did this. This is not acetic acid. What is this called? Acetate. And so don't get confused here. Make sure. We need KBs. These are bases. But if we look at this one, the Ka for acetic acid is 10 to the minus 5, 1.8. This one is going to be a lot bigger. Why? This is much, much more acidic than that. Why is that? Well, we look at methyl is kind of electron rich. And what is this? This would be like a trichloromethyl. And what's the oxidation state on this carbon here? The oxidation state on this carbon is -3. The oxidation state on this carbon is +3, quite electron poor. So this is going to suck electron density away from the carboxylic acid group here and make this one much more blue. Bases, we want red. Acids, we want blue. Even having one chlorine here, this is kind of weird. Substitution may strongly affect acid strength. These are bases. If we're looking at the conjugate acids, okay, you can look. But let's compare the base strength. Which one is a stronger base? A or B? A is stronger base. B. If A is stronger base, then this conjugate acid will be weaker. And so we should see this conjugate acid, which is acetic acid, is weaker, 10 to the minus 5, versus this one. Chloroacetic acid is 100 times stronger. Trichloroacetic acid is, again, borderline strong or strong. So let me go back to this here. What we say is that the negative charge is localized. However, in phenoxide, and I'm going to do something in organic chemistry, they often leave off the hydrogens, not because they aren't there. They're there. They just don't write them sometimes. But maybe I'll write them here. Like this. This charge is resonance delocalized. So what we can do here is we can drop these into the bond here and then kick these out and place them. So we're going to change the hybridization on carbon from sp2 to sp3 and then throw a lone pair on there. And the structure that we end up with here, this would be a resonance form, is going to look like this. Oops, let me make room for the lone pair here. It's going to distort the ring. The ring is no longer going to be flat like a pancake. It's going to have a kink in the ring now due to this sp3 screwing up all the sp2s. Here. This carbon they give a name to in organic chemistry. This one's called the ortho carbon. Or the ortho position. We have two ortho positions. This is also an ortho carbon here. It's ortho. This is called meta. We have two metas. Relative to the oxygen. And then we only have one para. The para is on the opposite end of the oxygen. And so we have ortho meta para. And so right now the negative charge is on the ortho carbon. But we can further delocalize this into the ring. And so what I'm going to do is I'm going to drop these into the bond here and then kick these out onto the para. So what we end up with is this structure here. Okay, and then we could drop these lone pair into this bond here and kick this lone pair out. I mean, not lone pair, bonding pair out. I'm going to kick these out onto this carbon here. And then finally, I'm going to drop these lone pair into this bond and then kick out this. And that takes me back to where I started. Okay. So what that does is it helps stabilize the negative charge. It makes it less red. In other words, the more we could spread out that negative charge, the more dilute it becomes and the less reactive it is. And so as far as bases go, this is a much weaker base than this. This is a powerful base, or I called it powerful initially. I'll just call it strong base. This is a strong base. And they're more powerful bases than ethoxide. But this is a weak base. It's a weaker, much weaker base. That means its conjugate acid is much stronger. So let's go back to the quiz here. So we have an electron withdrawer. This one's attached to the meta position. This one's attached to the para position. It makes a difference. Which one do you think? Because, I mean, this part is the same. And so what we're looking at is, first we look at bond strength. It's an OH bond, same, right? Then we look at polarity. Well, you know, this is a carbon, that's a carbon. Comparable polarity. You know, everything's kind of bonded. There's a bunch of carbons and a nitro, a bunch of carbons and a nitro. Then we look at the stability of the conjugate base. When we look at the stability of the conjugate base, which one's going to have a more stable conjugate base? Having the electron withdraw in the para position, because where does does negative charge ever land on a meta position? Take a look at all the resonance forms I drew. Did the negative charge ever land on a meta? No. The negative charge was either on an ortho or a para. And so having an electron withdrawer on an ortho or para will help do what? Okay, there's two types of delocalization I mentioned. What were the two types of delocalization I mentioned? The most important was resonance, and the second one was inductive effect. So in terms of the inductive effect, this is going to be good. But if I have a nitro, then the charge can be delocalized. So if this carbon has a negative lone pair and a negative charge, that lone pair can go here and then kick out these electrons here. So not only can we have inductive effect, that is the +3 or the +1, depending on which one you want to use, either the oxidation state or the formal charge. It's going to have an inductive effect withdrawing electron cloud and a resonance delocalization here. And so the para for sure is going to be it. Not only that, we can think of this one as being more electron withdrawing because we have the nitro on this one being more electron withdrawing. So this would make this slightly more polar. Because the ring we should think it's a hydrocarbon, so we should think of it as electron pusher, but because of the bonding the benzene ring, it's considered electron withdrawal because we can have, so it's kind of weird. In the ortho and para, look at all the resonance structures I drew. It only goes on the ortho para. Any questions on that?
I was going to ask, can you also think of it as, since it's more like spread out, that it can be like easier to read the electron, so that it's just strong around more so.
The more it's spread out, the easier it is to lose what?
To like pull the electron from it, rather than if it's like closer.
Pull the electron. When we're thinking about acids, we're pulling the hydrogen.
I think that as well.
The hydrogen?
Yeah.
Yeah, that's one way. The more electron withdrawing, the more polar, the easier it is to pull the hydrogen off for a base. The more electron withdrawing. I guess you could think of it in that way too. All right, so number 10, this is a problem I think we did in class, or a similar one. pH for a solution containing 10 to the minus 5 molar HCN must be solved simultaneously.
That's true. It's a weak acid and it's very dilute, and so you should have two contributors of hydronium. You know, Ka and Kw. And since it's such a small concentration, we have to worry about simultaneous. If it were a strong acid, we don't. So here we have a strong acid. We don't have to do this simultaneously. Step 1 won't be perturbed. Number 11 is not. 12. pH for a solution containing 1 times 10 minus 0.1 molar. This is phenylamine or aniline. Must be solved simultaneously. Kb is 10 to the minus. This is kind of high. The concentration is 10 to the minus 10. The Kb is really small, but this one doesn't. But if you're uncertain, you could just try it and see. That's what I did. Tried it and
Wait, so if you did want to solve it, just like look at it, is it because Kb is smaller than the concentration?
It's because this concentration is fairly high, 0.1. 0.1 molar, most likely.
So does Kb have to do anything?
Yeah, Kb does. We're going to form very little hydroxide, but we still have a lot
Okay.
of initial solution. So that's pretty much the reason why. 11 we did in class. That doesn't have to be solved simultaneously. Both 10 and 11, I did examples of that in class. I don't know. I changed the numbers a little bit for 10, but 11 is exactly the same number I used in class. So just look at your notes for that. Or watch the video if you didn't get the notes for that. 13. Ka2 for 0.10 molar succinic acid does not contribute a significant amount of hydronium. So if we look at Ka1 is 10 to the minus 5, oops, Ka2 is 10 to the minus 6. 10 to the minus 5 and 10 to the minus 6, those are pretty close. So this is debatable here. You know, if this were like 3 orders of magnitude smaller, there would be no question that I wouldn't. And so this one, since they're kind of close, you might expect both of them to be significant contributors. So if you put false here, I probably would have given you full credit. I probably gave full credit for both answers on this test because it's debatable. The way to figure it out is just to do it and see. So step 1 would be Ka1, step 2 would be Ka2. 14, the pH for 0.1 molar HF. HF is a weak acid. If it were a strong acid, it'd be A. And since B is impossible. I mean, C is not possible. B is, you can't get more. The B, it's a weak acid, so it's got to be greater than 1. All right, so here's the aniline. So aniline was, do I have to solve this simultaneously? So I just did a quick calculation just to see, do I need to solve this simultaneously? So I'd like to solve this stepwise, but it depends on x here comes out to. So I solved this for x using the simplifying assumption. Now if you solve it using the simplifying assumption, you have to justify it. And so I didn't justify it here. You need to justify it on your test. But this is just a quick check of the multiple choice. Since it's multiple choice, I'm not grading you on work here. And so the pH came out to 8.3. One we have to worry about Kw is when the pH is close to 7. If the pH is close to 7, then Kw is going to be important as well. But let's see this. Then I went on to step 2 here, just to see. In step 2, I came up and I did the simplifying assumption here in step 2, and I looked at the percent change. The percent change is only 0.25%. So with the 0.25%, we can say that step 2 is not so significant. 0.25%. But it's still debatable because it's still a 0.25%. A 0.25% is a 0.25%. And so I would have given them both, probably. So it wasn't so clear cut. All right, the pH for 6 molar sodium chloride should be 7. You know, sodium ions and chloride ions are neutral, or considered neutral.
16 pH for sodium hydroxide. This is going to be very basic. So this is going to give you a pOH of 1, so the pH is 14. Here we don't have to really consider Kw, it's a negligible contributor. 17 pH for 0.1 molar ammonium chloride. Ammonium is an acid, chloride is neutral, so this should be less than 7. pH for 1 times 10 to the minus 9 molar HCl is, well, it's 10 to the minus 9 molar H plus, which would give you a pH of 9, but pH of 9, is that possible for an acid? It's impossible. And so this is very dilute. It's primarily water, the contributor for hydronium here. So D is the correct answer. 19, what must be the molarity of ammonia if its solution has a pH of 11? So if you have a bottle of, a couple of things for this question. One, if you have a bottle that's labeled 6 molar ammonia, is that 6 molar the initial ammonia concentration, what they dumped in there, or the equilibrium concentration? It's the initial. If you have a bottle that's labeled 6 molar acetic acid, is that the equilibrium acetic acid concentration or the initial when they put the acetic? It's the initial. So whenever we do a solution, like what must be the molarity of ammonia, this is referring to the initial concentration of the ammonia, not the equilibrium concentration of ammonia. And the pH is kind of high. The pH is 11. So if the pH is that high, then water is going to be a negligible contributor, to this. I mean, the base is going to be the major contributor. So what we could do is we could just do step 1 and reverse it. So that's what I did here. I just did step 1 and reversed it. We're solving for the initial ammonia and the change here. So we can solve for the equilibrium ammonia concentration and then work backwards. So we work backwards by adding X to get the initial here. And so a lot of people gave me the equilibrium. That's not what I wanted. And a lot of people use the simplifying assumption. If you use the simplifying assumption automatically, you have to justify it. I didn't use the simplifying assumption because the math wasn't too terrible. So I went ahead and did not ignore this. I just went ahead and used it. Or it was 0.1, I think it was. But I made a little statement here. I said the hydroxide is already so high, 10 to the minus 3, that the hydroxide in the solution should come from the ammonia and Kw. But Kw should be negligible because the most you're going to get is less than 10 to the minus 7. And we already have 10 to the minus 3, so it's going to be a lot less. And so this is my justification for ignoring step 2, which is Kw. But I didn't use the simplifying assumption to calculate this. But if you did use if you use the simplifying assumption, the simplifying assumption is just used to calculate X. It's not used to tell you what the equilibrium is. So if we use that to calculate X, we still have to do the ammonia minus X. We still have to do that step. Okay, that's one. All right, number 20, which is this. Okay, step 1 is fine. Step 1 is H2S plus H2O. But what a lot of people did was they screwed up step 2. When we have an acid solution like this, we start off with the biggest hydronium ion contributor. The biggest hydronium ion contributor is going to be step 1, or Ka1 here, correct? But now we go to this. The problem is this. Most people did step 2 is Ka2. If I look at Ka2, Ka2 is 10 to the minus 19. So step 2 is either HS minus or water. When I look at water, the Kw, which is equal to Ka, which is equal to Kb, is 10 to the minus 14. Which is bigger? 10 to the minus 19 or 10 to the minus 14? 10 to the minus 14 is 100,000 times bigger. Which one's going to produce more hydronium? 10 to the minus 19 or 10 to the minus 14? 10 to the minus 14. Nobody got this, so I didn't deduct anything. But your step 2 is supposed to be Kw. That's going to produce a lot more hydronium than Ka2. So it's kind of weird. It goes Ka1 for H2S, followed by Kw, followed by Ka2 for H2S. That's the sequence it should have gone. And then you would have figured out all the species in solution. So we would have went from step 1 to this. This is our correct step 2, and then we go here, and then we go to step 3, which I didn't finish step 3. I didn't post this, so I thought, let's figure it. So this is why I called it the partial key. Partial key because you can complete it here. After step 2 comes step 3. I'm asking you for everything in solution. If I'm asking you for the equilibrium concentrations for all species, you have to do all the steps. You know, you can't ignore Kw, and you have to tell me the concentrations of all the species. You can't, you know, a lot of people just say, okay, X is equal to this. Well, I'm not asking for X, I'm asking for the concentration of all the species. Okay, the final problem here was number 21, or the bonus. The bonus, this one was tricky. Okay, number 1, this is the unusually strong acid. It's not so strong, it's pK at 10, which is 10 minus 10. But compared to other alcohols, this is quite a bit stronger, a million times stronger than ethanol as far as an acid goes. So we're looking at phenol here. And this is a very low concentration. When we see a low concentration of a weak acid, then we have to worry about Kw, right? And so some people didn't do Kw at all. That's not good. We have to worry about Kw. And some people did Kw, but they did it stepwise. If you do it stepwise, what do you have to worry about? You have to worry about step 2 perturbing step 1. If step 2 perturbs step 1 significantly, then we have to solve it simultaneously. And so the best answer for this is simultaneous. Ka for phenol plus Kw, simultaneous. So you should set up as a simultaneous. If you did it stepwise, and a lot of people did the simplifying assumption, but the simplifying assumption fails. You know, did you check it? The percent change? You know, be careful with the simplifying assumption. If you do it, you don't use it without checking. But anyway, you can see here, I didn't, actually, I just did this in my calculator, but basically step 1 we get this much hydronium. In step 2 we add 98. In step 2 we generate a heck of a lot more hydronium, and so we end up with 101. And therefore step 2 perturbs step 1. This must be solved simultaneously. All right, well, I'm out of time, so we'll stop here. If you have more questions, I have my office hour tonight.